In this lesson, we're going to talk about some applications of the dot product. Now, before we get into applications, let's just remind ourselves what the dot product is. If we've got two vectors, A and B, and we're going to do the dot product of them, we can do it in one of two ways. If they're algebraic vectors, we could multiply the components and add them up. If they were geometric vectors, we could do the magnitude of A times the magnitude of B times the cosine of the angle between them. And using this geometric interpretation leads us to one important point here. What happens if A and B are perpendicular? If A and B are perpendicular, the angle between them is 90 degrees. So when we work out what the dot product is, well, the cosine of 90 degrees is, of course, 0. So if two vectors are perpendicular to each other, their dot product will be 0. Okay? So that's an easy way of checking to see if two vectors are perpendicular. You do the dot product and see if it works out to 0. Okay. So let's move on to these applications here. There are only two applications that we have to look at. The first one is projections, and the second one is the concept of work. Now, projections are very closely related to sort of what the definition of the dot product is. So what I'm going to do here, hopefully, on this page, is we'll start by taking a look at what projections are in terms of geometric vectors, and sort of work our way down towards the formula that you need to know to do the projections of algebraic vectors. Okay. So first off, the definition here. The projection of a vector A onto vector B, we're going to use this notation here to indicate a projection. Projection, PROJ, subscript, angle A, and then another vector B. So what we're doing is we're projecting the vector A onto the vector B. And what we mean when we do a projection is the projection of A onto B is just that part of A, vector A, that lies parallel to vector B. Okay? So the way you can envision a projection is, imagine you've got two vectors here, A and B, with some angle between them, theta. Imagine taking a very, very bright light and shining it down so that these rays of light are perpendicular to that second vector B. This vector A here is going to cast a shadow on vector B. The line of the shadow is just going to kind of come down like this. Okay? It's going to form a vector down here. We'll call this C. C here is the projection of A onto B. Okay? So in other words, it's the part of A that is pointing in the same direction as B. Now, we talked about this in the last lesson when we were learning about what the dot product is. So you can already probably guess that there should be a way of figuring out what this projection is in terms of the dot product. And that's where we're going to here. But first, in geometric terms, we know how to use trigonometry to figure out what the magnitude of this vector C is. Okay? We know that the magnitude of C down here is just going to be the magnitude of A times the cosine of the angle between them. Okay? A cos theta. Now, what about, like this C here is a direction. So we've got, is a vector. So we've got the magnitude of it. What about the direction? I should just say direction. Okay. Well, the direction that C is pointing in is always sort of given by this vector B over here. Whatever direction B is pointing us, because we're taking the component of A that is in the same direction as B, or along that same line, C is always going to be in the same direction as B. So our direction, we can just use B hat. Now, B hat, remember, is a unit vector. So it's like we're taking B and we're just taking the directional part of B here. Okay? So B hat, we've divided B by its magnitude, and it just says B hat is just a way of saying something that points in the direction of B. Okay? Now, what happens, so we can put these two halves together and we can say that C, the projection of A onto B, is equal to A cos theta, magnitude of A cos theta, B hat. Okay. Now, what happens if we have the situation that we have over here on the right, where the angle between the two of them is greater than 90 degrees? Well, if we imagine our bright light shining down here, we can imagine the shadow cast by A. Is the shadow, in this case, is going to kind of come out like this. Okay, it's going to go in the opposite direction that B is pointing. Okay. Does this formula still work? Well, let's see. What's going to happen if we calculate the cosine of this angle theta? Okay. Angle is greater than 90 degrees. Cosine of theta is going to be what? Positive or negative? We're now into quadrant 2, so this angle is going to be a negative. Okay. So if theta is greater than 90 degrees, cos theta has got to be less than 0. Okay. So we're going to get a negative sign coming out when we do this. When we do take the cosine here. So if we do, basically, this formula is still going to work out. C is still going to be the magnitude of A times cosine theta. Okay? Cosine theta is going to be negative. And if B hat is pointing in this way, negative B hat is going to be pointing in the opposite direction. Okay? So whichever way, whether this angle theta is greater than 90 degrees or less than 90 degrees, we can still use this formula here to get that vector C. Okay. All right, so if this formula here is the projection of A onto B, let's just start here. The projection of A onto B is magnitude A cos theta B hat. Okay. How can we turn this into something that we can that allows us to use those algebraic vectors to do the projection? Okay. Well, what we know is that let's pick a color here. We know that if we do our dot product, A dot B, that's the magnitude of A times the magnitude of B times the cosine theta. Okay. What we want is A cos theta here. So we've got A cos theta appearing inside this formula here. We've got A times B cos theta appearing in here. So let's just divide through by B. So we get A cos theta on the right-hand side. On the left-hand side, we're going to have A dot B divided by the magnitude of B. Okay. The other piece that we have is we've got this B hat here. Okay, this unit vector B. So what's another way of calculating this unit vector B? Well, to take the formula for a unit vector is just your vector divided by the magnitude of your vector. So we can take this expression, sub it in here, this expression, sub it in right there, and get a new formula for the projection of A onto B. The projection of A onto B is going to be, instead of A cos theta, we're going to have A dot B divided by the magnitude of B. And instead of B hat, we're going to have vector B divided by the magnitude of B. Okay. And then we can simplify this a little bit. Projection of A onto B is going to be A dot B divided by the magnitude of B squared, multiplying these two magnitudes of B together, times vector B. All right. So that's the formula that the textbook gives you for the projection of A onto B. Okay? A dot B divided by B squared times B. Now they give you a second formula too for the magnitude of that projection. Okay. Okay. Which is the magnitude of A dot B divided by the magnitude of B. Okay. Okay. So these are the two formulas that you basically need to know. Okay. How do they get from one to the other? Well, you can see here we're just taking the magnitude of the numerator here, magnitude of A dot B, and then if we take the magnitude of this B term here, we get another magnitude B, so they cancel out a magnitude B and a magnitude B to get just one magnitude B down on the bottom. Okay. All right, so let's take a look at an example of how you're actually going to use this thing. Okay. Here's our example. Find the projection of C onto D if C is 2, -7 and D is 9/12. So what we're going to start with is the formula for a projection. Projection of C onto D. And we want to use that formula that we ended up with at the end of the last slide. So C dot D divided by magnitude of D squared times vector D. And we could just work out what each of the parts of this formula are separately. We can say, all right, I want C dot D up here, so let's work out C dot D. Well, that's going to be 2, -7 dotted with 9/12. We'll multiply our x components. 2 times 9 is 18, plus -7 times 12, which is -84. And 18 plus -84 is going to give us -66. Down in the denominator, we have the magnitude of D, so we can work out what the magnitude of D is. That's going to be the square root of, let's see, our x component is 9, so 9 squared plus 12 squared. Or the square root of, let's see, 9 squared is 81 plus 144, or the square root of 225. Okay. And then we can just put all this together into our projection formula. So the projection of C onto D is going to be negative 66 divided by, I'm sorry, I'm missing a squared in this formula, aren't I? D squared, magnitude of D squared. So if we square the square root of 225, we just get 225. And then we want to multiply this by vector D. Well, vector D is just 912. So now we're just doing scalar multiplication. We're taking this fraction here, negative 66 over 225, and multiplying it by the vector 912. So this is something we can just punch into our calculator. Negative 66 divided by 225 times 9 gives us negative 2.64. Negative 66 divided by 225 times 12 gives us negative 3.52. So the vector, which is the projection of vector C onto D, would be this algebraic vector here, negative 2.64, negative 3.52. Okay, our last application here is the concept of work. Now, you've probably encountered work before if you've done physics, okay? I've just put the definition of work up here. Work is done whenever a force acts on an object as it undergoes a displacement. Only the component of the force in the same or the opposite direction to the displacement does work. Okay, so here we have the idea that we're only interested in the component of the force that is in the same direction as our other vector, our displacement vector. Okay, so this is where the dot product comes in. Okay. So we've got some force, F. We've got some displacement, D, which is our other direction. If we want the work done, we want to multiply these two in such a way that we're only multiplying the components that are in the same direction as the displacement. So our work is just the dot product of our force and our displacement, or F dot D. Okay. Where F is our force measured in newtons, D is our displacement measured in meters, and W is the work, and work is measured in joules. So if we're given two algebraic vectors, we can just do the dot product. If we're given two geometric vectors, we can use our geometric form of the dot product, magnitude F, magnitude D, times the cosine of the angle between them. Okay. So let's just take a look at an example here. So let's take a look at this example here. We have a storage box, which is being dragged up a 3.5 meter long ramp, inclined, the ramp is inclined 24 degrees to the floor by a force of 4.3 newtons. That's the force that's doing the dragging. The force is applied at an angle of 38 degrees to the floor. How much work is done by the force? Well, we're given magnitudes of our force and displacement. The displacement is 3.5 meters. And we're given these angles here. So we know that we're going to do work. We're going to be using this form of our work equation that involves magnitudes and angles. So we know that our force, or our work, is going to be magnitude F, magnitude D, times the cosine of theta. And theta, of course, is the angle between the force and the displacement. So all we need to do is work out which of these angles we need to put into this formula here. And the way to figure this out, I think, is to draw yourself a diagram. So I'm going to start by putting in the floor here. Nice and shiny. Okay. I'm going to put in my ramp, okay, which is inclined at an angle of 24 degrees to the floor. Okay. And I am going to put in my box. Okay. And I made this a box because that's about the only thing I can draw is a box. And I've got a force. So this force is being applied to this. I'm going to do the force in another color. My force will be red here. So my force is being applied to my box at an angle of 38 degrees to the floor. So I'll just do that like that. So I can label that as 38 degrees. And this is my force. I know that the magnitude of the force is 43 newtons. Okay. So I've drawn in my one force, my one vector, my force vector here. The other vector involved here is my displacement vector. So I have to get my displacement vector, I have to think about what path is this crate going to follow as it's being dragged. So applying this force, we're dragging it along. It is going to travel along the ramp. So that is my displacement. It's going to move sort of in the same direction as the ramp. Okay. The magnitude of that displacement is going to be 3.5 meters. Okay. What about this angle theta? Well, theta is the angle between my force and my displacement vector. So theta has got to be this angle right in here. Okay. Conveniently enough, my force vector and my displacement vector are tail to tail, and that's how we want them oriented whenever we're talking about the angle between them. So the angle between my force vector and my displacement vector is going to be, well, let's see. We don't know what it is. We have to figure out what it is. We know that from the force vector to the floor is 38 degrees. From the ramp to the floor is 24 degrees. But because our displacement vector is right along our ramp there, that's also the angle between the displacement vector and the floor. So what do we need to do to calculate theta? What do we need to do with these two angles? We know this one here. We know this one here, 38 degrees. What do we need to calculate theta? What do we need to do to these two angles? Multiply them, generate a random number, take the derivative. What? What do you think? Yeah, we just need to subtract them. We know that from here down is 38, from here down is 24, so this little part in between them, we got to do our old friend subtraction. So we do 38 minus 24, and we get something resembling 14 degrees. And from here, we just plug it in. Magnitude of the force is 43. Magnitude of the displacement is 35. Cosine, 14 degrees. Punch all this into our calculator, and we end up with, I think we end up with 146 joules. Okay? And that is the work being done. As long as our force is in Newton and our distance is in meters, this works out to be joules. Okay? And we are done.